team here, one after the other each day. We just flipped orders this time, so theory and experiment. But I'm also going to flip topics a little bit. But both of us have made the same decision, and that is to go and look at an application of what we've been doing. And so I'm going to talk some about applications, but within the same context of everything I've been talking about so far. So I will still use the generation of high harmonics as the underlying program. So I'm going to cover three things. I'm going to cover orbital tomography. And I left you hanging about the issue about this. I'm going to come back and just remind you of where I left off last time to begin with. Then I'm going to move from there to photochemical dynamics and show you how you can apply these really broadband pulses to advantage in looking at photochemical dynamics. And then finally, I'm going to address, is there any chance of doing anything interesting in condensed space? Of course, I wouldn't do this if I wasn't going to answer it yes. So you know the answer to the question that I put up there. Now, I put this figure up very close to the end of my last talk. And I want you to look at it for a minute. This is an interferometer. If I make this a spectrograph there, and I put an image of a spectrum, actually I took it from a photoelectron spectrum, but it's a spectrum as a function of time delay. If I make it, that's a frog setup, and I think the first lecture I told you that we can measure E as a function of T, amplitude and phase, all aspects of the pulse, using a frog setup, which is an interferometer, a nonlinear interferometer. I didn't show you, but I think you would accept if we could do it E as a function of T, we could do E as a function of X by making the shear in space, and in fact that's true. So we can take a pulse and characterize it completely, amplitude and phase, from only the amplitude information that you have in the image. So the challenge is, can we make similar measurements of, well, the thing that's involved in this, molecular orbitals or molecular wave functions, and molecular dynamics, and actually, in fact, attosecond pulses as they're being formed, because they're also being formed in an interferometer-like way. Let me now jump to the interferometer that underlies attosecond generation. You've seen this image before. There's a wave function, a wave packet that's pulled out, comes back, and there's an interference between the wave packet and the wave function. An interferometer made by light, but an equally precise interferometer to the interferometer we're used to with ordinary light. It's precise in the sense that we can move the arms of the interferometer. We can move the arms of the interferometer by adding a second color, polarized parallel. Actually, you've heard this a few places now here. People haven't described it always in these terms, but you've heard about adding another color and the advantage that that can be. You could also bring it in at a different angle, and you've heard me talk a little bit about coming in at a different angle, and you make a gradient. You could also come in with a different polarization and bring the electron in at a different angle. There's all kinds of ways you can manipulate this underlying interferometer that's below high harmonic generation. Here I want to also add something else. Instead of having just a simple atom like a hydrogen atom that's been applied, we could replace that with a molecule, a nitrogen molecule, for example, and that's what I'm going to do in a minute, or a bromine molecule. I'm going to do in a few minutes more. And that molecule we could choose to align in some different way. I show you an angular distribution of alignments. I'll show you in a few minutes how I get that. And you could imagine moving that, in other words, removing the wave function from which we start. And in some sense, that's moving the arms of the interferometer as well. And so we can do all of those things. And so we should be able to set up, and I talk about how the interference and how you measure that interference. So you recognize this figure. These three figures are all So the radiation that we observe is reading that interferometer as it is generating high harmonics or attosecond pulses that we've talked about everywhere else. I want to go back again and emphasize how it's reading it. It's reading it through the transition moment or the dipole moment. The dipole moment is what's induced by the interference, and that dipole moment in the strong field approximation. That's the approximation that once the electron is free, you can ignore the Coulomb potential. The dipole moment in that approximation is the integral of the wave function times r times the recollision electron wave back at e to the I kx, now assumed a plane wave, coming back again e to the I omega t, and then some amplitude to represent the amplitude of each k. In some sense, the only uncertainty here is the wave function from which it came. You might say, you could imagine the plane wave, we know, we can measure it. We measure the frequencies for sure, and we can induce the plane wave with the k vector. And the amplitude could be measured in some other way. Okay, so now I want to go on and leave you exactly where I left at the end, and you've probably been thinking about it. And so, where do you stand on measuring molecular orbital wave functions? So, some say that orbitals are intrinsically unmeasurable. Let me repeat why they say it. They say there is no such thing as any electron going around in an orbital. Electrons, there are many electrons in any system in which we're talking about, like a nitrogen molecule. All these electrons are identical. They're interchanging with each other all the time. There is no such thing as an electron in an orbital, and therefore, it's a mathematical construction, the argument goes. It isn't real. You can't expect to think of an electron in this orbital, and of course it's unmeasurable. And I think chemists are taught that. I really do. I think this is a natural thing that everybody is taught. I think less clearly people say you can't measure a wave function. There are ways, I think. But it's, I think chemists had felt quite strongly that you can't measure orbitals. So I don't know what you think about it. I said, think about it before you go. I want to talk about the experiment. So I'm going to show you an experiment. I'm going to give you the arguments for why it works. And I'm going to show you the degree to which we can say something about the orbital and even talk about the kind of orbital that we measure. Okay, so I'm going to start on it. It's going to be molecules now. You've heard a little bit about molecules from Lars Madsen in his talk earlier. And you even heard a little bit about alignment. I want to just briefly say how it works. So maybe I'll repeat what he said before, but I'm only going to say it very briefly. He said it much better and much longer. Imagine you have a jet of gases. Think of those as the nitrogen, jet of molecules. Think of those as nitrogen molecules. That's what we're going to use for now. Let's imagine we bring a beam of light into that, linearly polarized, whose intensity is strong but not ionizing, up to but not over the ionization, up to but not over. This induces dipole moments inside the system. The dipole moment interacts with the field, causing a torque towards an alignment or a potential well in some directions of alignment for the molecule. Think of the molecule like this. Think of the laser field as along here. The electrons can be biased to one side or to the other side, depending on how the field is going. The dipole, thereby induced, interacts with the field, and that's the polarizability, and there's a starship associated with it. And molecules are pulled towards an alignment by that strong laser field, and you can see what they would look like after they've moved to the middle of the potential of such a field. Since this pulse that we interact with it is short, we can choose the pulse length so that the molecules see this potential well, fall into it, and we turn it off right at the end of it. It's a bit like a pendular problem. Think of all kinds of pendula sticking here. Imagine there's no gravity. We turn it on, they all start towards the ground, and then we turn off gravity when they get close to the ground. And anything within these small angles that allow them all to come together, like in a pendulum, will be aligned, and that's what happens in this. It's really a pendulum problem. Now we have the molecules aligned, and of course, molecules have a spectrum, a rotational spectrum, that leads to periodic realignment, periodic structure of how this rotational wave packet flows. So if we do an experiment with a pump pulse that comes in whose purpose is to align a molecule, we can come at any other delay afterwards, knowing how the rotational wave packet evolves, and interact with that pulse, creating harmonics and probing it thereby. And that's the experiment. You understand the experiment, and you understand, hopefully, qualitatively, the alignment process. Stop me if you wish anywhere like before. Okay, so how well can we do this? This was some time ago that we did. We could probably do considerably better now. How well we can do this? You saw this one. I just took it up in one of the earlier slides to show this is a Coulomb explosion image of the nitrogen molecule. We've gone rotationally aligned it, waited until it got to as best alignment we can get. We come with an intense pulse. We pull off a whole set of electrons simultaneously. And we look at the ions as they fly apart by their Coulomb repulsion so fast that they can no longer move anything except repel each other. This process, in this case, we look at nitrogen 3+ and 2+, I believe it is, making it a full 5+ for the ion, overcoming, we hope, all bonding, or dominating all bonding that's left in the molecule. This is a distribution of the probabilities of seeing fragments go in different directions. So small probability this way, large probability this way. The molecule is aligned with the distribution roughly as you see it. This is a 2D projection. By changing the polarization of the light, we can change the alignment of the molecule, and there's a whole set of, I think, 4, 6, 8, 16 of them. So that's the degree of an alignment we're going to use in the experiment I'm going to show you. This is done, actually we probably do a little better in the experiment I'm going to show you. This is done by an effusive jet of gas going into a vacuum chamber, very low density in this case, and then we explode the molecule. In the experiment I'm going to show you, we use a supersonic jet, so it may be a cooler distribution to start with, although we keep the density somewhat high in order to make harmonics so it isn't fully cold. Okay, now what's the concept now? We know how to align molecules. We know how whole idea of interference. I think the concept is caught here in an artistic rendition by somebody who wasn't a scientist. And so this is you have to think of it as a cartoon. And this is the cartoon version of the HOMO orbital of a nitrogen molecule, where blue and red represent the opposite phases of the wave function, arbitrarily labeled plus and minus. There's no plus and minus, of course. They're just arbitrary labels. And where the molecule is aligned in this image along the direction of the laser polarization. And this image is meant to show you the recollision electron wave packet coming back. You know that it chirps. The electron wavelength or energy in the beginning and the middle and the end differ. And caught here is the middle, and by the artistic way the artist has set it up, you can see that the wavelength is approximately the structure size of that orbital. Now you can think about interference, and I want you to think about it as I talk along. You can imagine what that interference might look like when the wavelength was longer than the structure size. It would be different. There would be modulations going on inside it as the wavelength moved around. Different kinds of modulation. Equally, it will be different when the wave packet becomes bluer. And so the radiation that we see will have to be different. Of course, that's what we're seeing in a high harmonics. It's just the words to tell you what you're seeing. Now think about taking this distribution, since now you know we can align the molecule and rotating it through 90 degrees. I don't have an image for that, but you can all think about interference, and think about the interference and how much different it must look if we have the molecule aligned like this when the wave packet goes back, or like this when the wave packet comes back. And all other alignments, you saw what we can do for alignment. Actually, that should make you think a little bit about tomography. I put a picture of a tomograph, medical tomography I pick off the internet, just to make you think about it. And that's the basic idea that's behind the molecular imaging of orbitals. So we said, okay, let's set up an experiment and look at high harmonic generation in this way. Let's look at high harmonic generation where we control the molecule with the degree of control I showed you. And that's done with a 2-pulse experiment then. We start out with a pump pulse. The pump pulse, in this case, is 60 femtoseconds in duration. Its intensity is 5 times 10 to the 13 watts per square centimeter. And it's focused from a relatively small beam coming into the target chamber, leading to a relatively large focus where the gas jet is formed. The gas comes out of a supersonic jet. We estimate the temperature to be somewhere on the order, but it's a pretty soft estimate, on the order of 20 degrees Kelvin. And the gas jet densities and length are quite short. I think the length is about 200 microns of the gas jet, and we work in a place where we don't make much harmonic conversion. The issue is not harmonic conversion, but to see the process. We want phase matching to play a minimum role in the process. The probe pulse, which is going to make high harmonic generation, must be more intense. Its intensity is 1.5 times 10 to the 14. Its duration is shorter, it's about 30 femtoseconds. And so it comes in and it's focused from a larger size outside and therefore to a smaller size inside, hoping to overcome and have uniformly illuminated sample, uniformly aligned sample in the center. The beam then, the harmonic beam is then brought out and picked up at a microchannel plate off the grating. And this is a typical harmonic spectrum that you see. It's actually, we go from, say, the 15th harmonic to around the 39th harmonic. In fact, we go a little further. In this case, you see the 39th harmonic. In other words, photon energy of 23 eV up to about 60, and actually slightly beyond. Now, it's not the wavelength of the light that's kind of important here, but it's the wavelength of the electron. So 100 eV, the wavelength of the electron is in the order of an angstrom. Okay, so the electron is doing the interference. So the underlying electron wavelength is in the order of an angstrom. Now I'm going to show you the data that we see. The data that we see is here. It's almost raw data. It's not quite. We have, as you remember from the transition moment, we have to know something about the amplitude of the wave packet coming back at each frequency. And so we either have to measure it or calibrate it out. What we choose to do is to calibrate it out by using an atom as a reference, an atom that is almost identical in its ionization properties to nitrogen. And that's argon. There's been many studies of argon versus nitrogen, and they ionize very similarly aside from the details of ionization as a function of angle, and it's not very, that's not so strong. So we use argon as a reference. So what we see is the raw data here for nitrogen as a function of angle, where argon is used as a reference, but of course argon doesn't change as a function of angle. It's a constant reference. And we assume that we know the argon orbital in calculation, or in the experiment. So here's harmonic number again, plotted across here. I told you we go beyond harmonic 39. In fact, it's up to harmonic 43, and it starts at harmonic 17. There's 19 different projections here. I'm sure you don't want to look at each one. I think the only thing to look at is the very different and unusual structure of this and how it changes as a function of angle. You see a minimum in this region, and you see peaks in other regions. And so we use this data with the assumptions of polarization, which were then not measured, since they have been measured and the assumptions we use are correct. An assumption that there's a phase jump here at the minimum that was then not measured and has been measured now, and our assumption was approximately correct. And using that, we put it into a tomographic algorithm to reconstruct the wave packet. The tomographic algorithm is just a tomographic algorithm that's been developed by others. It's nothing to do with us. We just put it in the algorithm. It assumes a plane wave coming back again, just like you would have in ordinary tomography, because light can be done that way. It assumes a plane wave coming back, and here's the reconstruction of the nitrogen orbital that comes from those 19 different projections, just directly out of the tomographic algorithm with the assumptions only that I mentioned. Here it is, so you see immediately the 3 lobes that you know are there in the wave function, and that was there in the artistic sketch. This is a 1 electron Hartree-Fock calculation of what it might look like. I think it's better to compare it with the following. This is a multi-electron calculation, a more sophisticated calculation of what the ionic spectrum should be, but also filtered by the fact that the maximum energy of the electron coming back again corresponds to giving us a harmonic number of about 65 eV, what we have in the experiment. You can see that there's a great deal of similarity. Of course, we see the nodes where they should be no matter what. We see the 3 lobes where they should be. We see the basic structure where we should be for the multi-electron effect. We see halos around it experimentally. I'm sure those are not real, but of course we're making a plane wave approximation to an electron that's coming into a Coulomb potential and therefore is being distorted. And there's clearly errors that come in here. There's clearly errors that come in here. However, we get the amplitude and relative phase. It's the wave function, not the wave function squared. In other words, we know that the phase here and here are different. Of course, there's an absolute phase that we do not know. It does not make sense to even talk about. And so just like in optics, there's no absolute phase. There's no absolute phase here as well. So in that sense, anyway, otherwise we see the wave function, not the wave function squared. So this is the tomographic picture of the molecule. You might like to say, okay, what have we really measured? What kind of orbital? Because when you begin to look into it, there are multiple orbitals, and chemists think of it one way, and other people think of it another way. So let's place what we've heard all so far in a multi-electron language. The experiment makes, of course, I've said all the time, a superposition of it takes a wave packet and splits it in 2. A wave function splits it in 2, keeping a wave function and a wave packet in a continuum. Let me say it differently. We have the molecule intact. The n-electron wave function is one of the superposition. And we have a molecule in which we have n-1 electrons in the ion and 1 electron in the continuum. And that's the superposition. And we see the difference between the n and the n-1 electron wave function. It's the Dyson orbital. We look at the Dyson orbital, the difference between the n and the n-1 wave function of the molecule. Let me just say a few things about what you see. Since tunneling selects the initial state, we must return to the same state or to a state that is coherently related to this initial state. If it selects 2 or 3 states, then these 2 or 3 states you can return to by the electron wave packet. And that leads to interesting potentials for looking at dynamics. It's launched by the process of tunneling, but I will not go there. I will not talk about that any further. So this is the orbital tomography that I set up for you in the first place. And you might want to look at it critically and say, okay, does it work? Is this real? And have we found a way to measure an orbital? Or maybe not exactly a chemist's orbital, but it looks exactly what, it looks like what they would have in all of their textbooks, I'm going to keep going if there's no other questions. I'm going to just make a jump now to electrodynamics.
I don't really follow the argument that you haven't done what you said you've done. I don't understand the argument why it shouldn't be able to be done. I don't understand the objection to your research as presented. I feel like if I understood it better, then maybe I would be able to understand, what, I feel like there's something that I'm missing that other people are objecting to.
In a way, I think maybe I overstate the objection. So let me comment on this a bit. What I said is correct as far as I know. The chemists are taught that orbitals are unmeasurable. And so when this paper came out, I spoke at Yale not long ago, and the professor said he was ready to give the exam. I mean, it was just right at the end of the term. And students, he saw this paper, and students began to ask him about it. He put a question on the exam about it. And they had huge discussions around at Yale about whether this was a measurement of the orbital or not. People from Dudley Hirschbach called me from Harvard and said, this is really amazing. They never thought an orbital could possibly be measured. And this will change how chemists are taught about orbitals in general. So, I mean, chemists have accepted this to a large extent, that this is a measurement of an orbital, although maybe slightly different orbital than the orbital they normally think about. It's a Dyson orbital, it's a well-defined orbital. So maybe I overstate that it's uncertain. However, I have given talks where people are very, very, very disturbed by even saying, did you think you can measure an orbital? I had a man that stood up at the end of the talk that I gave in Vancouver and said that this was just garbage science and it shouldn't be given. And he actually wrote to the president of the National Research Council where I worked at the time. I'm now at University of Ottawa for not the same reason. And he said I should be fired. He said I should be fired. He did. The letter said I should be fired. But fortunately they didn't fire me.
Paul, if you could go to the next slide. My reservation is with point 2, okay, not with the experiment, just the theoretical aspect. So with an n-1 bound molecular orbitals and one continuum orbital, no theory can ever produce an exact wave function. It's always a matter of a representation, because I have an infinite number of continuum states which this extra electron occupies. Therefore, whether I can say that the theory can reproduce an exact wave function, I think it's here is not applicable. I'm only referring to the theory, not the experiment. That's my concern.
I'm not sure if you're saying the same thing. I might say that it's not transparent here that we create a relaxed ion. We pull the electron out of the ion, and is it really
it's relaxed? A matter of representation.
Which is what would be the Dyson orbital. It's a relaxed ion versus the relaxed molecule.
Yeah, and then the theory would produce, upon a representation of these orbitals, a wave function. And another theory will produce another wave function, and so on and so forth. They can agree up to 16 significant digits in their bound state energies or the wave function energy, but they can never be the same. That's my point 1. I think it's I tend to agree. For N2, it's possible that produce an N electron bound molecular wave function. That's mine.
There's another aspect that's come up. There's many aspects of quantum computing since this experiment came through, and people have worked on it to a certain extent. So we now know, which we didn't know then, that it's possible that when you ionize, you have a significant chance of pulling out an electron from a deeper level. Actually, Lars mentioned that earlier. I think it was you. Maybe it was somebody else. I think it was you. So tunneling takes not only the top electron in a system, even maybe like nitrogen, for sure like nitrogen, but also deeper bound electrons. You might find that hard to accept because we all know that tunneling is exquisitely sensitive to the barrier height, and there's a significant difference in IP on the level of IP between, say, the HOMO, which is what we're measuring here, and the HOMO -1 of nitrogen. However, we're ionizing at an incredibly fast rate, even if we